Okay, thank you for the invitation. This is my first ever talk in a conference, so I'm very nervous. So be patient. Okay, so, well, that's the title. And I'm going to start giving the motivation of the problem. And I'll say it, well, let me know if it's too small, the handwriting. So I'm going to start with the basic definition, which was due to Dwadi and Hubbard, of what is a polynomial-like map. So basically, you just have two disks in the complex plane. So you have U prime containing U. They're both topological disks. It's compactly contained, in fact. And then you have a map, F, that is going to map U prime into U holomorphically as a degree V cover of degree bigger than 1. And and it's a proper map. So it's nothing else but a map. There'll be some F here. This is U prime, and this is U. Yeah. So this is the basic idea of what a polynomial-like map is. And then what complex bounds are geometric restrictions on these domains. So for example, okay, the easy one is, for example, you have U, and then you have U prime, and then you ask for the moduli of U prime, U minus U prime, to be bigger than some constant, okay? If you don't know what moduli is, I'm going to define it. Just imagine this is actually an annuli. So imagine that you actually have just two rounded disks. This is 0, and then you have R1, and then you have R2. And then let's call G the ring between these two, okay? So that'll be G. And then you define the moduli of this as 1 over 2 pi, the logarithm of the quotient between R2 and R1, okay? So when R1, the radius of R1 tends to 0, this grows, and when it tends to R2, this tends to 0, okay? So that is just for a round ring, but there's a way of generalizing it for topological disks, okay? So this is the basic principle. This only has one domain. We're going to work with things that are slightly more complicated, but this is the basic idea, okay? And I'm going to first talk about some of the applications, and then I'm going to explain the results. Application. No idea if it has two P's. Maybe it doesn't. Okay, so the first one I want to talk about is renormalization conductors. Pablo was talking a bit about this problem yesterday, so I'm going to try to approach it in a slightly different way so it's less tedious to hear it again. So basically, it was around the 70s that Feigenbaum, I'm sorry, dyslexia. Baum, and Colette and Treser. So they discovered that there's some universal behavior of unimodal maps that go through a period doubling cascade. So for example, imagine you have, this is kind of the classical example, you have the map X that goes to AX, AX, 1 minus X, and the parameter here is A, yeah? So it's a real parameter. And then, okay, so when A is close to 0, the maps are like this, and then it starts like coming up like this, yeah? So it's well known that they go through a period doubling cascade, and what happens is, for some parameters, and hopefully this one will work, is that there is a periodic interval. So the critical point comes back after 2 iterates. And then, hopefully this doesn't look that bad. So the second iterate will be something, I don't know, like this, okay? Oh, no. This is a fixed point. Yeah? So the second iterate inside this box, again, looks like a unimodal map. So just restrict yourself to looking inside this interval I. Yes? So when you move the parameter, the point where the critical point either moves down or moves up. So you could rescale these and get again something that looks like the original family. So what happens is they realize that there is a parameter here where the critical point is fixed. Yeah, it's a period 2 fixed point, well, a periodic 2 orbit. So I'll call those parameters, let's say Bn is a parameter, so it's a parameter, such that what happens, the critical point, so I'll call it C of Bn, so it's the critical point of the map corresponding to that parameter, is a periodic point of period 2 to the n. Yes, so the first one will be when this is actually like here. No, this is when the critical point is fixed under the second iterate, and then consecutive, like well, there are also the parameters when you zoom in, then it will be period 4 inside here. So what they discovered, like numerical estimates, show the following. So that the limit when n tends to infinity of the sequence of these parameters, so this ratio, minus b and minus 1, converges to 1 over delta. And even though the limit where the parameters tend as a sequence, depends on the family, this value is universal. So it seems to be independent of the one, like the family of unimodal maps you take. And the idea was, well, what's the explanation for behavior like this, as you can see in all families, with constants that don't seem to depend on them, no? And so there was, at the beginning, some numerical proofs of what is going on here. But it was until the 90s, I'll say, that Sullivan gave a more conceptual proof of what's actually happening. And the idea is to study the map that sends, that rescales this map again to a map that looks exactly like the original one. So you just rescale this interval 0, 1 again and flip it. So it's the map that is sending these restrictions to maps that are in the original family. And so Sullivan gave a conceptual proof of the fact that these constants are universal. And it's basically, there's a hyperbolic fixed point for the renormalization operator, which is the one that turns these boxes into like the rescaling. And the hyperbolic fixed point has some eigenvalue, and the eigenvalue turns out to be this constant that you can see in all the families. I'm not going to talk more about like the proof or anything, but the idea behind this requires you to consider this kind of maps. So, and to prove complex bounds for them. So that's the first motivation. It's related to that. And then, well, and other people, it's not only Sullivan. So like a full proof is to have, well, Macmillan and Lubitsch, but and it is more general than just this period doubling, but I'm not going to talk about that. And okay, so another application of this could be, I think it's been mentioned a lot as well. What is density of hyperbolicity? So this problem could be seen both in the complex plane and on smooth case. So in the complex, it's called factor conjecture. And basically, I'm going to state it in the complex, but okay, I will say something about the smooth case. So you would take a map acting on the Riemann sphere, and it's going to be a rational map of degree D. And then you define the field Julia set of Q, which is equal to the points such that the iterates of those points stay bounded for all n. Yeah, so the forward iterates of points that don't escape. And then the Julia set is the boundary of this set. So a map is called hyperbolic if it's expanding on this set, or there's many definitions, equivalent definitions. I'm just going to write one that is easy, which is that all critical points of Q tend to a periodic attractor on their iteration. Yes, there are different equivalent ones. I'm going to stick to this one for the time being. And then, well, the question is, these maps are easy to understand? Well, easy. They're the best understood. And the idea will be, well, is it possible to approximate any rational map of degree D by maps that are hyperbolic? And it turns out that in the complex, I think the conjecture is still kind of wide open. But in the smooth case, the analogous problem is already been settled. So in the smooth case, well, something that might be interesting, I don't know, is that it's known that the set of non-hyperbolic maps has positive measure. For example, so it could be that it will be dense, but it is known that it's not going to be like, well, it's not going to have full measure, for example. Yes? Well, and there's other results about structural stability, but I'm not going to talk about that. And then in the case of smooth maps, which maybe you're more familiar with, so it was Newhouse, so there's like bad news, I don't know. Has like showed in the 70s that hyperbolic maps are not going to be dense in any space that of dimension bigger than 2. Yeah? So that has already been known for quite some time, and a big question for a while, I don't know why it's been done now, but it was, question is, what about dimension 1? So it turns out that both in the complex and dimension 1 are more rigid, so there is kind of hope for hyperbolicity to be dense. Bigger dimensions, there's too many things that you can do, so you don't get it. And then it was done by Jacobson for C1 topology. Then it took, I think, around 30 years. Shen did it for C2 topology, the proof of density of hyperbolicity, and it was Kozlowski. Oh, I always get this name wrong as well. I'm really sorry. Shen and Banstrian prove density of hyperbolicity for all the case and real analytic. So yeah, good news in dimension 1. Density of hyperbolicity, it's true. And the idea behind Jacobson's proof is more like perturbations. But it turns out that it's not going to work for higher degrees of regularity, and both these proofs rely heavily on the use of complex tools, and in particular of some sort of generalization of polynomial-like maps. Okay, and then it can also be used to prove local connectivity of some Julia sets, but I'm not going to motivate that. So that's another application. Connectivity of Julia sets. And what Sebastian was talking about, quasi-conformal rigidity, which is something that Pablo was talking as well yesterday, so I'm not going to go to the definitions. So it is a very useful tool, and the aim of my talk is, instead of, I want you to like clarify what they are and the basic idea of how to get them. It's very technical, so I think the intuition behind it is quite clear. So I'll try to make it clear for you what the idea is behind it and hide all the details so you feel like you understood everything. So I hope I managed to do that. So my talk will be for, I hate this. It's focused on explaining mainly just this. Just that. This result, okay? So this is joint work with Trevor Clark and Sebastian Benstrin, which is my supervisor. So the result, I'm not just going to read it, and then we're going to go through it slowly. So it's that, okay, first, I'm sorry, I had to delete the hypotheses because it was too long. So I'm going to write I'm going to write them here. So what's the setting? Sorry, stop looking at it now. Okay, the setting is the following. We have F from M to M, a real analytic map. So it's just locally it's a Taylor expansion. Analytic. And M is contained in R, is a closed interval. So it's one-dimensional dynamics. So this is multimodal, no? And what we're going to have is everything that appears there, that critical point. So we're going to have F is persistently recurrent. And on omega of C. Omega of C is, so you take a critical point, it'll be C is a critical point of F. And this is the omega limit set, normal omega limit set. And for people who know more about this area, this persistent recurrence means that each puzzle piece has only finitely many children. But if you don't know that, this implies that the omega limit set is minimal, and actually, in fact, the critical point, the definition we're taking is non-periodic. So imagine for the time being that you have an omega limit set that is minimal, and the critical point is non-periodic, so it accumulates on itself, but it's not a periodic orbit, okay? So I think morally just think about it like that. So infinitely renormalizable maps and maps with strange structures out there. But okay, so that's the setting. So we have a critical point, it's persistently recurrent, a real analytic map, and then, we get there. So we want to show that there exists a universal Bow constant. So the constant is only going to depend on the number of critical points and the order. So not specifically on the map. Any map with sort of that vector of critical points will have the same bound. Combinatorially defined intervals such that the diameter tends to 0. I'm going to define this set in a minute. So there's a set around the critical points in the same omega limit set so that this happens. Okay, so I'm going to just explain bit by bit what this means instead of me trying to just wave my hands right now. So I'm going to start from the bottom. I'm going to define what this I hat is. Okay. So take an interval I containing M, will be called nice, if you know that all the iterates, if it's open, and all the iterates of its boundary never lie inside the interval. So they have some sort of dynamic meaning. Sorry, yes. Very important, yeah. So never lie inside the set, okay? A very easy way of constructing one is just take a fixed point and the pre-image, for example. This interval will be nice, this interval will be nice, this interval will be nice. If you take pre-images, that will still hold. So we're going to assume that we have a nice interval that is really small. And I'm going to define the first return map to an interval. So take a point x in my space and assume that there exists some k such that the iterate fk of x lies in my interval I. So there's an interval here, I have fk of x, and I don't know, consider the full orbit, so this fk minus 1 of x is somewhere, that goes here under f, and I don't know, things happen, no? And then you have x here. So what you do is you consider the inverse images of this interval following the orbit of this point, okay? I'm going to define this as gk because I'm going to label them using the same index here. Then gk minus 1, so there's an interval here, which is the component, the connected component that contains this point of nothing else than the inverse image of the previous one. Yes? And then you do it again. So now you take, for example, I'll get to the last one. G0 is just the component that contains x of f minus 1 of the previous one, which is G1. So you're just picking the way that you're taking the pre-images. So remember, our map is not injective, so there's not a unique pre-image. So I'm just specifying how I'm taking the pre-images. So a thing like this, I to k, what is 0, is called a chain. And each element, gi, is called a pullback of I. Now, if the interval is nice, pullbacks of the interval have nice properties. For example, any two pullbacks of a nice interval are either nested or disjoint. And that will be a quality that we would like to have. Let me see if I'm forgetting something. Okay, in particular, if our point x, to begin with, was in I, then G0 will be, okay, and k is minimal, such that fk of x is in I. So the first time that you come back to the interval, then we're going to denote G0 by the landing domain of x to I. So this is the points that return to your interval at the same time as your point x does. And, okay, so then we're going to define that L hat thingy there. So L hat of x of I is nothing else but I, if your point x is in I, and the landing domain of x to I, if your point x is not in I. Okay, so that's the set. So we have an interval, we consider the points that come back to it, and we associate some domains. So we have I, and we're only going to consider this for the other critical points that are in the same omega limit set. So imagine this contains a critical point, and there's, for the time being, just another critical point in its omega limit set, C prime. If this interval is small, then there's a landing domains of C prime to I. And that's because it's minimal. So, well, and then the same omega limit set, so obviously it's going to come back. Okay, so this is the set. So you have an interval. For every critical point that in the same omega limit set, you get a different interval. And now what we want to do is to extend the first return map to this set to something that is complex in something similar to that. So the idea is the following. So the first return map, what is it? We're only going to consider the first return map. So first return restricted to omega of C. So the only points that we're going to care about are the points that are in the same omega limit set as our critical point. So what happens is I take C, and in this case, for example, let's imagine that C first enters this interval before returning. Yeah? So there is here a landing domain of C to this I hat. Yes? So there is just some interval that corresponds to the points that enter here at the same time, and that is some fk. So the same thing you do for the points here. So this point, well, I don't know, let's say enter here, and there are different iterate fn. All the points in this interval will enter the set at the same time. And let's assume that we have another one. So let's say that there's another point in the omega limit set, x here, x in omega of c intersection I. That as well, I don't know. Let's assume that it returns first to this interval, okay? So there's a landing domain of x to I, and then this is this is some fm. So this is a multi-valued map. So you have a set of intervals, and then you want, for each of them, you just define the first time that the point enters this union of intervals. Yeah, so it's a different iterate for each of these domains. So fk doesn't have to be the same as n or anything like that. Yeah? So that's the first return map. Define a set, consider first time points return to this set, and consider these iterates. So this is a real map, and now what we want to do is to construct a complex extension of this picture. And the way to do it is the following. So F, remember, is real analytic. Which means that it's expressed locally as a Taylor expansion. So you have M, and F is defined in the real, but the same Taylor expansion locally will give you a complex analytic map on a neighborhood. Now, let's say U in the complex plane now. Yeah, so it's just exactly the same expansion, it's just evaluated in complex points. Yeah, so, but this map is not globally defined. So if our interval is small enough, it makes sense to talk about this. So imagine for the time being that the interval is really small. And now every time I say F, I'm going to think about the complex extension of F, which is the same map, but it's locally, okay? So what I want to do is, can I find domains that contain this? So the range will be, can you see green? I don't know, it's one of those things that maybe some colors are not clear. So for each of the critical points, in this case, so we have C. So the green ones will be the range. And then for this one, there will be another ball here containing this other critical point, C prime. Yes, so the map is going to be F. Okay, yeah. Okay, so the map F, which is going to be now a complex map, is going to go from B, which will be the union of the green things, to some U. Let me find a color that I hope you can see. Maybe this one. To some U. So the idea is, now for each landing domain, I have to find now a disk here, a disk here, and now the map that is going to send this one to this one has to be that iterate of the map. Yes? So this purple ball will get sent as a holomorphic covering to the green one under this map, which is the first return to the interval. So what you do is you already have the real picture, and now you want to find domains that will do that. In this case, this one will be both in the domain and in the range. Okay, so I'm gonna, so both B, B is equal to the union of some BIs. In this case, let's say it's B0 and B1. So BI are topological disks. Each of them contains only one critical point. So BI contains only one critical point of F. And the same, the UIs will be as well topological disks. And now the map is going to map, so F of some UI will get mapped as a covering to some bj. So for example, this one gets mapped as a covering to this other one. Yeah? Yeah, sorry. Yeah, thank you. It's just, I started the other way around, everything goes wrong. Okay, yeah, sorry, yeah. So each of these ones, so F restricted to some UI, it's a holomorphic proper covering with only one critical point. In our case, so there's only finitely many critical points. So always, the BI is going to have only finitely many connected components, okay? So because remember, each of them contains only one and exactly one critical point of the omega limit set. And UI, a priori, could have countably many connected components depending on the omega limit set. But in the case when it's persistently recurrent, you only have finitely many of them. So in this case, it's going to have both of these sets. So B has the cardinality of the curly B is equal to the number of critical points of F intersection omega of C. So each of the critical points in the omega limit set gets a domain in the range, and the other ones, you don't know how many they are, but they're finite. And this is what we call a complex box mapping. So a complex box mapping is a generalization of this idea in the sense that it just has more domains, but the basic idea of how the things get mapped to each other is the same. So that's what I mean by the first return map to this I hat has a complex extension. Now there is some other stuff, which are the bounds. So we don't only want to build this, but we want to ask for some geometric conditions on the way this is built. So I'll have to split it in two cases, which says F is non-renormalizable and renormalizable. I'll be very quick on explaining how this works. So take your interval I. It's a nice interval. And then you construct a sequence that is called the principal nest. So the principal nest, so you have I, contains the critical point. So let's assume that C is in here. And so there's the critical point. And then I1, so I0, 0 will be equal to I. I1 will be equal to the landing domain containing the critical point to I. So C returns, there's a landing domain here, and then you take I1. And now you take, again, now we consider I2, which is nothing else but the landing of C, now to I1. So this will give you a sequence of intervals that are nested around this thing. I2, and then you can carry on. So there's two possibilities. Either there exists some n in n such that when, okay, wait a second. So the return map, I'm going to define it. I'm going to just have some notation for it. So the map, so I will call the return of IN restricted to C, the map that sends the landing domain containing C to IN to the interval IN. So remember, this map can change, but I'm going to call it the return map. So it changes. It could potentially change. You don't know how long it's going to take it to return. But it is a map, and I'm going to denote it like that. So the return map to this point, and in that particular point. So there are two choices. It happens that the return to IN of the critical point always lies in the next one. So you kind of, when the critical point returns to here, comes back, returns to I, comes back in here. And when you consider the return to this one, returns to this one. And so, yes, so you always return to the interval that you're defining as the landing domain. And if that happens, then you call this interval I to be terminating. And in this case, the intersection of all these is a periodic interval. And yes, so and it's renormalizable. The intersection of all the INs. This one is periodic. And the map is renormalizable. So if this happens, I'm going to call it terminating, which is the second case. So if the map is renormalizable at that point, then what you will get is only one domain. You will get something like this. And if your map is, well, and then if this doesn't happen, what is? That it exists. And then the other option is that there exists some n in n such that the return map to IN of the critical point is not in the next one. So that's the only two possibilities. Your map is renormalizable. Sorry, yeah. Sorry. Yes. Yeah, I'm sorry. So yeah, either for all, you land in here, or there exists one where you escape. Yeah? So if you stay there forever, there's going to be an interval, there is a periodic interval, and your map will be renormalizable. Or your map is non-renormalizable, and well, at this level, because there could be deeper renormalization, but you're just looking at this interval. Okay? So those are the dichotomies. And depending on which kind of interval you started with, you can get different maps. So in one of them, this will only have one domain, and in the other one, it will be something like this one. And I'm going to try to explain what the bounds are. Okay. So, yeah, I'm literally just going to explain those bullet points there. So remember, the complex bounds are geometric conditions on these domains. So, well, the first one is clear. So you want the components of the domain to intersect the real line only on the intervals that you already had on the real line. So you don't want to add any new points in the real line. So basically it means that if you have the domain B, which was green, and let's say this is I, well, there's some stitches here, and those points are not there. So this is nothing very fancy. And then the other one, you want that these domains. So what does nice mean? It means that the moduli between the purple ones and the green ones is going to be uniformly bounded by a constant. And it doesn't matter how small this is. So what you want is to find a universal constant that will work for infinitely many intervals I. And what you want to do is to be able to generate that. So the problem is to prove, maybe not that it exists one, the problem is to prove that the constants are universal and it will hold, it doesn't matter which scale you take. And to be free, it's a bit more technical, but it basically means that if you take one of the domains, B, there exists two disks, which I'm going to call P minus and P plus, which I think this color will be invisible, and P plus, that one outside and one inside, this moduli big, and there's no post-critical set here. So there's no point of the omega limit set of the critical point in all this region. So what you want is to have good control of where the post-critical set lies with respect to your domains. And this is very useful for applications, even though now it seems a bit dark. So I still have 15 minutes. So I'm going to explain you the most basic idea of how to construct something like this. So you have the real first return map, and then what do you do? So the basic idea is very, very easy, and then you wonder why it will be so difficult to prove. So first, there's nothing, so we have the interval I, we have, let's say, a point x that returns to I under this iterate. So remember, that gives us a chain. So you have the map f here, you have fk minus 1 of f, and then you have this until you get to x. Yeah? So the very basic principle is what you want is if I can find a domain, but now in the complex plane, and then I'll just take the preimages. Like the same thing that you did in the real line, now you want to do it in the complex plane. So you start taking the preimages, I don't know, don't pay too much attention to the drawing, and then you end up having a preimage here. This has to be very small, okay? So and then what would the aim be? If you're very lucky, and this one, let's say that this one is the landing domain. This is the landing domain of x to I. So you have the interval I here. You have a smaller interval in here. And if you're very lucky, then the first, when you take the pullback, it's inside here. If you do that, then this map already has all the properties, all the analytic properties that you want, except from the fact that it will be unicritical, but don't forget about that. So this will get mapped as a covering into this other domain. Yes? So the idea is very simple. If you manage to have this inside, then you already have the analytic properties that you want. And then you like to get the bounds. But the first problem is to do that. The first problem is, what can I take here? So when I take the pullbacks, I can make sure that this is inside. And so that's the vast majority of the proof is just based on trying to actually get it inside. Now I'm going to try to explain what are the problems. So it seems very easy, like why would it be so complicated to do something like this? And the first thing I want to say is if you have a polynomial, the things that you use as these domains are the pieces of a Joker's puzzle. But in this case, we don't have a Joker's puzzle because our map is not globally defined. So we'll have to find domains by hand to pull back. So that's the first kind of big difference between the polynomial case and the real analytic one, that there's no basic structure to start with. Okay? Okay. So this is the basic principle, and I'm going to just pinpoint the main steps on the proof and try to say why they're necessary. So the proof of how to do something like that. The first thing that you need to do is to find intervals, to find a sequence of intervals that I'll denote by IN. Remember, the theorem says that we can do it at arbitrarily small scales. So what I'm going to do is to build a sequence of intervals that tend to 0 and try to build it for each of these, IN in N, that can be used as building blocks, okay? So basically, the real intervals are the ones that are going to define these itinerary things. Yeah, so you want to find intervals. But then, okay, then you have to prove something that is called real bounds. And this is where most of the work goes into the paper, I think. So the real bounds are essentially is that geometric, if you have good geometry, let's say, on the real line, then this will give you good geometry on the complex plane. This is morally what it means. I'm going to just explain a tiny bit of why would this be necessary. So basically, you have to find the intervals, prove properties for the intervals. If you can prove properties for the intervals, then any good property for the intervals, you'll be able to sort of promote it to taking the pullbacks of disks with those intervals as the base. Yes? And then it will be very, I'll be very brief. And I'll just explain, well, I don't know if I'll have time. I think. So I'm going to say which are the disks that you want to take. So there is some sort of choice of domains in the complex plane that you want to start doing the pullbacks that are called Poincaré disks. So basically, you have the complex plane and an interval I containing R. That is just going to be open for the time being. And then you consider this set, C of I, which is equal to the points in the complex plane minus the real line minus this interval. Okay? So it's the complex plane minus the real line. So the only part of the real line that you see is the interval that you already had. So this is a hyperbolic Riemann surface, and it has a metric. And with this metric, you consider balls that will be called Poincaré disks. So they're defined like, well, D will be the hyperbolic metric on this space, C of I. And now I want to consider certain balls. So it looks fancy, but it will make sense once you see the picture. I think the picture is very clear and the definition. It's a bit eh. So you take the points in this space, in C of I, such that the distance, this hyperbolic distance, between these points and the interval I that you have is actually less than some R of theta. So R is a function. So let's say this is the radius, and there is a function. I'm not gonna say the specifics. It's just some log of tangent or something. But this is ugly. But it's just the points whose distance to the interval is less than something in the hyperbolic metric. And theta will be just an angle between 0 and pi over 2. And 2 pi. So these balls, you're very lucky, and the way they look is they're just Euclidean disks where the angle that they intersect the real line is exactly theta. So the angle of this disk and the real line is theta, and the same with the other one. So even though the definition might not be really nice, the geometric shape of them is very easy. So what we want is to use these disks as the building blocks. So what you want to do is to use Poincaré disks as the green domains, and then you just want to study what happens when you take an interval, and then you start taking pre-images under a map of a thing that is just like this. Something very easy to see is, just by this angle thing, is that if theta prime is smaller than theta, then the d theta prime I will contain the d theta of I. So as the angle gets smaller, the disks get bigger. So it's the same base, but the disk is bigger. So if everything was very nice, if the map we had was defined on the whole space, what happens is that you have the Schwarz Lemma. So what the Schwarz Lemma tells you is that actually, if you take a map that is univalent, but it's globally defined, then you take one of these disks, the image is contains something that has exactly the same angle. Yeah? So that's good. Like, you have very good control of the shape of this thing. But that's only when you have maps that are globally defined, which is not what we have. So the problem is, these things will get a bit distorted. And they will get distorted, and I have it here for you to look at. So this is, the Faria de Melo have this estimate of how the shape changes when you have a map that is not globally defined. And, okay, the statement is complicated, but I think the idea is simple. So how distorted they get is just proportional to the size of the interval. So the smaller you go, they're almost like nothing happened. So you take a Poincare disk here. So yeah, theta, the theta I. Then you map it forward by some f. I don't know, yeah, f. And then you will lose some angle. So you know that the image is, I don't know, somewhere here. But the angle, now, the new angle that contains it, so the theta prime of f of I, you know, is proportional to the size. So the smaller you go, the better the map gets. So if you want to control things and you want to control the shape, you have to go to very small scales to fight the fact that this map is not actually going to just not change the disks. Because even if we have a differ now, so imagine that you don't even see any critical points, but your chain is very long, then your map will distort things. So it could potentially not even land inside. And then another thing, okay, I'll just say this one, is, and another easy thing to see, I think, is what happens when you, okay, that's when the map is univalent. What happens when you have a critical point? So imagine that you have I'll just, let's say this is minus 1, 1, and then you have this Poincare disk here. So it's this theta I. And this is 0, and let's imagine that the map is locally like set square. And we want to take the preimage of this disk under set square. So what happens is, forget my term, well, don't pay too much attention to the shape. So you have the preimage, it will be something like this, no? It gets mapped like a 2 cover. But then, okay, so maybe you can say, okay, this is minus 1, 1, and I can put it inside a disk with some angle, yeah? The theta prime, let's say, of minus 1, 1. But what happens if the critical point is very close to the boundary? So here it looks like it's doable. It doesn't seem to be too much of a problem. But the problem is that in the complex plane, let's imagine that, well, and this will be very, let's imagine, because the scale, so let's imagine that we have 0 and some epsilon very small here, and this is 1. And our disk now lies here. Let's say here. So now what happens? If I take the preimage of this under the same map, a lot of the line is going to go into the complex plane. And the base is going to be very small compared. Yes, so now I'll have something like very small on the base, like the real trace, and a lot of it will go to the complex plane. I'm just exaggerating, yeah? So this is the way the preimage looks. But now we'll have a very small base, and then we'll need to pick a very big angle here so we can, so we know where this is. So it will be inside something, but potentially, since this is very small, the angle here will have to be way bigger. So something that is important, and this is what you have to work with the real bounds. So the real bounds gives you, for example, if you have good control of where the postcritical set lies inside these intervals, then you have better hope of knowing what's going on here. Because in the complex plane, you do have this, yeah? And basically, it's just that. I think the basic principle is you have this, you want to pull back, and the problem is where is the postcritical set and how can you manage to control this? And yeah, so I think the idea is simple, but it is very intricate to actually do it. And the difficulty is not only do it for one, but find universal constants that will work for all maps in the same class. So yeah, I guess that's it.